Good morning, everyone, or good day, or good evening, or afternoon, depending on where you are. This is Chris, the Ancient Scholar. So today, what I want to talk about is I want to go back and talk about some physics, respiratory physics, to be more exact. And this will be in the respiratory physics playlist. And this is something that relates to gas laws. And we've done a pretty thorough introduction to the gas laws on the physics playlist. And I think hopefully most people have a pretty good handle on the gas laws themselves, and when we look at the gas laws, I think we have to kind of look at the bottom line. What do they tell us? And really, what the gas laws tell us is they tell us how a gas behaves at a macroscopic level. What is it's a macro state, or what we call sometimes they'll call these state variables, or macro state variables, and obviously these are very helpful. There's no doubt that these are very helpful, and these include things like temperature and pressure and volume, and these are pretty well defined by the gas laws. There are obviously some limitations, and we model our gas laws off of the concept known as an ideal gas. And obviously we know that there is no such thing as a perfectly ideal gas in nature, but if we model things as if they are ideal gases, and we often do this in physics and chemistry or what have you, is we don't have a perfect model. It's something it's 100% accurate and precise, but we have something that does a reasonably good job of approximating what we really see, or what we can actually measure, and that's kind of what goes on here, certainly with the gas laws. Now, I just want to take this a little bit further, and I want to talk about a theory that we can use that actually complements the gas laws, and the gas laws are conceptually, at least, the picture that we get can be derived from this theory. And again, this theory is just a model. So it is not a 100% accurate and precise, and it doesn't describe nature, every aspect of nature, but it does a good job. It's a good approximation, and it'll provide us with a little more insight into what's going on. So this is known as the Kinetic Molecular Theory of gases. Okay, so big word. Let's try to break this down. So kinetic is obviously motion, movement. Molecular refers to molecules, because generally gases that we deal with in respiratory therapy are not single atoms. That is to say, we're not as interested in dealing with single atoms for the most part. There are things like helium that we sometimes deal with, but generally the gases that we deal with in respiratory therapy are going to be molecules. Be it a diatomic molecule of oxygen or a diatomic molecule of nitrogen, what have you, we're going to be dealing with molecules. So that's where the term molecular comes from. Now, this applies just the same for single atoms, like we're talking about helium as a gas. So that's kinetic molecular, and in theory, well, obviously, it's a theory. And it does help us explain the physical world fairly well. Now, there are 5 postulates, if you will, that define kinetic molecular theory, and I'll go ahead and go through them real quick. The first postulate is that a gas is a collection of tiny, tiny little particles. Small little particles, they all travel in more or less straight lines, they're in constant motion, and they obey Newton's laws. Now, we know that Newton's laws break down at some point when we talk about quantum mechanics. So, again, this is an approximation. 2, molecules in gas occupy no volume. That is to say that these molecules are individual little points. Now, the gas as a whole does occupy some sort of volume, but when we get away from looking at gas when we get away from looking at the macroscopic state of gas, okay, and we zoom in and we want to look at individual little particles of gas, what we do is we model it as, okay, they're just tiny little points and they really don't take up any space. And they're random motion, straight lines for the most part, And then we talk about the collisions between the molecules or atoms of gas when they collide, because they're all over the place, here and there and everywhere. When they collide, they have a perfectly elastic collision. And what does that mean? Well, most things collide in what we call inelastic, or an inelastic collision. That means that if you can imagine like a blob of slime, or two blobs of slime, and two blobs of slime collide, they kind of, what do? They kind of deform and merge into each other a little bit, and the energy that the individual blobs had when they collide is kind of dissipated, and goes away in the form of heat and all that, and there's a loss of energy, or basically we don't have conservation of energy. Now momentum is a product of mass and velocity. Obviously momentum is conserved, but energy is not. This is a very important point to appreciate when we talk about gases, is the fact that gases, we model them as if they didn't have that type of inelastic collision, and instead they have a perfectly elastic collision where the molecules will bounce into each other, and there'll be a perfectly elastic, they'll just bounce right back. There won't be any they won't deform, they won't smoosh together at all. They'll just collide, boom, hit, and go about their merry way. There's no loss of kinetic energy. Obviously momentum's conserved. So both energy and momentum are conserved in perfectly elastic collisions. And we need to have this occur in gases, because if a gas molecule were to have inelastic collisions every time it hits something, and these guys are moving around at 1,000 or more miles an hour at room temperature, so they're colliding all over the place. Every time they collided, they'd lose energy, and what would happen? Well, my gas, if I looked at my gas, well, what would the pressure do? The pressure would go down, and we don't see that, right? I can take a tank of gas, compressed gas, and assuming that I keep the temperature the same, and I have a little pressure gauge on that gas, that pressure doesn't change, and you can come back day after day after day, and for the most part, that the gas will stay there, and so it doesn't lose energy. So we need to model this as these molecules having perfectly elastic collisions. And what I did is I just kind of drew a little picture here describing the elastic collisions. So this is an inelastic collision. These are kind of like two blobs of slime. They kind of merge together, and basically merge together and deform, and they lose energy, and produce just kind of this big blob, versus a perfectly elastic collision where the two particles collide, bounce off each other. There's no loss of energy, and obviously no loss of momentum, and they go about their merry way. Now obviously these arrows are supposedly vectors, and you can see these are a little longer here. Obviously that's not, it'd all be the same, because there is no loss or gain of energy. So don't take this as a representation of real life. It's just kind of a picture to give you an idea of what's going on. Here I just have these little points of molecules or atoms of gas, and they're banging around, they're banging into each other, banging into the side of the container, the wall of the container, perfectly elastic collisions, just random movement. Okay, number 4, there are no repulsive or attractive forces between the individual molecules. Like a solid or a liquid, I have pretty significant intermolecular forces at play, and that holds the molecules together. And obviously I have something that's solid, or even liquid, with hydrogen bonding in water, for example, there's still fairly significant amount of intermolecular forces. That won't happen with gases in kinetic molecular theory. And then postulate number 5 is the average kinetic energy, so this is average, of a molecule is described as 3 kT divided by 2. T is the absolute temperature, and K is something called the Boltzmann's constant, or Boltzmann constant. And I just have that formula here, 3K T over 2. And obviously the Boltzmann constant plays a very important role in deriving the ideal gas equation, PV equals nRT. Okay guys, so that was an introduction to kinetic molecular theory, and kind of some of the theoretical basis behind how we derive some of these gas laws. Again, it is just a model, and there are certain limitations, and this model will break down under certain circumstances. Take care, and as always, thanks for hanging in there, guys.